So we looked at several steady state solutions like Ekman pumping, Ekman transport, Sverdrup transport, and so on. Let's look at an example of transient response, and the easiest one to look at is the so-called inertial circles. So assume that it's a horizontal pressure gradient that is 0, so grad eta of the sea level is 0. Sea level has no gradients, and the background state is stationary, so U and V are 0. And let's say we have no acceleration in the zonal direction when we start, and we will just create a forcing in the meridional direction with a wind stress that again dies off over the Ekman layer as delta Y or del Z, and that's the only thing that's forcing the ocean. So this is an example where basically something that is really observed can be explained with this system of idealized equations. So you force the ocean as a burst of meridional wind stress, and then it dies away, and then you have motion set in to look at what happens to Coriolis. So once wind stress forces a meridional current with this balance and the wind dies away, all you have left is then the Coriolis effect on the meridional current to the right of the direction of motion, which is then related to the zonal current, because the meridional wind stress and meridional currents are going to create zonal velocity. So du dt is Fv. So the zonal wind that was 0 and acceleration that was 0 now after the wind burst has a zonal acceleration that is related to the meridional currents that were created by this wind burst. And since we have taken off the winds now, there is no acceleration in the meridional direction at all. What do you get? So you have del u del t is F times V, and once you create the u because of this, then you again get Coriolis acting on the zonal currents, and you get a meridional acceleration happening after some time that is related to minus F times u. Notice that we have not considered friction here at all, and this is a realistic situation. Essentially what happens is when the ocean is forced with a burst of wind, the surface is always being forced with the winds because it hardly ever wind stresses hardly ever totally disappear. But when there is a burst of wind because of a let's say a little gust or little storm or whatever, the layers below in the thermocline can get forced by the wind when it's strong enough, because the momentum penetrates and sets the interior of the ocean in motion. And in the interior, away from the wind stress forcing, the friction is very small. Okay, so the wind gust happens, sets the deeper thermocline water in motion, and then the wind dies away, so the surface begins to respond to something else. But the current that is set in the thermocline now, because of inertia, will continue to move, and the Coriolis will act and create from the meridional current a zonal velocity. Zonal velocity then will again experience Coriolis and create another meridional acceleration, and so on. And you can show that just by taking Coriolis as the sole forcing, you can derive a circular motion out of this. So free motion in the northward direction V, zonal direction towards the east because of Coriolis, then southward flow because of the Coriolis acting on the zonal current, and so on. So if the currents are strong enough, then they can make these circles, and you can even derive the radius of the circle and so on. And these are actually observed in real data. Okay, so this is kind of an example of Hurricane Florence in 2018 that passed by, and inertial oscillations generated by Florence in It says 2018, but here it's 2019, obviously a mistake. The overview map here shows the path and the scale of Florence relative to the deployed buoys, floats. The inset map B here shows the detailed trajectories of the floats during and after the passage of Florence. Image of Florence taken by NOAA GEOS, and data is here from the autonomous air-launched autonomous micro-observers, which are used to study cyclones, ocean response, how deep the mixing happens, and so on and so forth. And you can see that the cyclone has passed by, and you can see the continuing inertial circles that then decay away after the cyclone has forced the floats here. So you can imagine how the inertial circle based on, so the cyclone obviously rotates in a clock and counterclockwise direction because it's a cyclone and rotating around a low pressure, so you can use your Coriolis to do that. Flow will be going from the high pressure outside to the interior, and you get rightward deflection, rightward deflection, rightward deflection, so you end up with counterclockwise circulation. So you can see the motion that is also approximately counterclockwise, but you can clearly see the inertial circles that are being traced by the transient response of the ocean to this gust of hurricane winds that pass very quickly. Unless it stalls, it basically moves fairly rapidly away. So the floats that are deployed into the hurricane by air launches, so you can go and just drop them into the eye of the hurricane to see how the wind speeds, ocean currents, ocean mixing, cooling following the hurricane and so on happen. But here we're just looking at the currents and a clear example of the inertial circles. Okay. The other thing we have to add is the so-called Kelvin and Rosby waves, which again, depending on the scale of the wind bursts and the scale of the forcing in terms of time and space, can generate waves in the ocean. So the perturbation in the ocean is propagated away from this location of the perturbation through waves, and there are mainly two types of waves, Kelvin waves and Rosby waves. So I forgot to turn on my laser pointer. So the schematic illustration of production of Kelvin and Rosby waves by temporarily westerly wind stress centered on the equator. This is very common in the Western Pacific, which tend to be associated with El Niños, for example. So if the wind burst is westerly, you can imagine that the Ekman currents are going to be towards the equator, because you push the water this way, Coriolis is going to push into the equator, push the water this way in the southern hemisphere, tilt towards the left, so you get convergence on the equator, which is a dynamic boundary because of Coriolis changing sign. Water doesn't easily cross the equator, so you end up with deeper thermocline, higher sea level propagating ahead of the wind burst, because the Kelvin wave, which is propagating here along the equator using the dynamic boundary at the equator, building pressure gradients on either side of the equator and creating a propagation solid like a Kelvin wave packet that has propagated eastward here and create a convergence on the equator. But at the same time you have wind stress curl. So if you look at the winds that are focused on the equator and you do your left hand and right hand rules in the southern and northern hemispheres, you also end up creating cyclones on either side. So you see that there is a low pressure center, low sea level, and low sea level on either side. So you have divergence lifting thermocline, lower sea level, as opposed to thermocline deepening and higher sea level here. So you can again use your potential vorticity arguments to show that this has to propagate westward. So if you have a circulation that is counterclockwise, you're going towards higher F here, lower F on this side. So to maintain its restoring force. Basically, you can think of it as vorticity conservation between relative and planetary vorticity, obviously as before, again making assumptions about the depth of the signal. Waves basically require a perturbation, which is given by the westerly wind burst, and a restoring force. Kelvin wave is called a gravity wave because gravity is the restoring force in this case, and Rosby wave is called a planetary wave where the Coriolis is a restoring force. So you can easily convince yourself as to why the Rosby wave has to propagate westward using the vorticity arguments here. And it turns out in the atmosphere, Rosby waves can propagate in all sorts of direction because the winds can Doppler shift the waves, and the waves can propagate clearly eastward, westward, northeastward, northwestward, and so on and so forth. When we saw the atmospheric response in chapter 5, I think, we saw a stationary Rosby wave pattern going from the West Pacific northeastward towards the US, for example. Okay, so that's kind of the end of the chapter. We are doing it in a very qualitative way here. If you want to read more of a mathematical treatise on equatorial waves, the Matsuno paper and the Gill papers, and there are numerous other papers like Dudley Shelton and Mike McFadden and so on, which discuss the Rosby and Kelvin waves in various situations like El Nino, La Nina, or MJOs, the Madden-Julian oscillations, and so on and so forth. So there are waves running around in the ocean all the time, but there are seasonal waves, there are interannual waves, and there are also intra-seasonal waves. And of course, you can also get Kelvin waves not only along the equator. It basically needs a boundary towards the right hand side in the northern hemisphere, towards the left hand side in the southern hemisphere, so the currents are converging onto the equator. In the case of westerly wind burst, you can also have an easterly wind burst and create an upwelling Kelvin wave which raises the thermocline as it goes eastward. When they hit the coast on the eastern boundary, in the northern hemisphere, it can go northward because now the coastline is on the right side, and it can go southward along the coast in the southern hemisphere because the coast is on the left side, as we need for the Coriolis in the southern hemisphere. So you also get coastal Kelvin waves which can be very coherent and go from the tropics during an El Nino all the way into the Gulf of Alaska, for example. And when the waves are very warm and very strong, in fact, some of the tropical fish can go with the waves all the way to Oregon and so on. So there have been examples of people catching tropical fish at very high latitudes during an El Nino because they just followed the warm Kelvin wave all the way up the coast. So I wanted to add a few more words before I close out this chapter. Where am I here? So we were talking about waves. When you try to explain the propagation direction of the waves, everybody uses slightly different explanations on how to get you to capture the physics of it. So for the Kelvin wave, which we said is propagating eastward, these anticyclonic flow around the high situated on the equator, you can think of as convergence because you don't get a full anticyclone on the equator. You have a dynamic boundary in the middle. So you are converging flow on the front end, and you are kind of taking away water on the back end of the Kelvin wave packet. So you are pushing the thermocline down behind and pushing it up down ahead and pushing it up behind. So you can think of a pressure gradient that gets created that is in the eastward direction, which then adds to the eastward propagation of the Kelvin waves, which is one way to think about why the Kelvin wave propagates eastward. Obviously, when you do waves, you have to derive dispersion relations for the phase speed, and then you have to look at the group velocity and see which way the phase is moving, which way the energy is moving. And in the tropics, atmosphere and ocean, you typically do it deriving shallow water equations, which are very useful, and they give you solutions. But then the solutions are also free waves, which are not really completely free in the real atmosphere and ocean. Nonetheless, you can take satellite data for sea surface heights and so on, and easily extract Kelvin waves and Rosby waves as well. So the relation from the waves, the physics to the waves, to the consequences in terms of the thermocline being pushed down and SST warming ahead of it, etc., are all very important, and these explanations should help. But if you remember that the Kelvin wave propagates eastward in the ocean and up the coast, then you are doing well. Similarly, for the Rosby wave, again, a little bit more complicated, but we have to go back to our potential vorticity conservation, because remember that the Kelvin wave is a gravity wave, where gravity is the restoring force. For Rosby wave, it's the vorticity and the beta effect, or the variation of F with latitude, that's very critical as a restoring force, often referred to as planetary wave as well. So here in the cyclonic circulation around the low here, in the ocean, low means you have raised thermocline and sea level high in the middle and dropping off away, just the opposite here, for example, but this is on the equator. So here you have a full cyclonic circulation of the equator. So you have water moving towards larger F in the wave, which means the water parcel has to acquire or reduced relative vorticity to maintain zeta plus F over H, assuming H is approximately constant. So you can take the reduced relative vorticity and see which way the flow has to be to satisfy this reduced vorticity, remembering that the vorticity is again defined as del V del X minus del U del Y. Right? So if you do that carefully on both sides, then you will convince yourself again as to why the Rosby wave packet moves westward when you take, for example, here F is increasing, relative vorticity has to decrease. Here F is decreasing, relative vorticity has to increase. So there is a corresponding change in circulation that you can infer that will make this wave propagate westward. Of course, if you do mathematically, then you will see it much more clearly in terms of the phase speed. So there are many details which we are skipping here in order to just explain this without any of the math. Okay? Let's leave it here and move to the coupled climate variability in the next podcast.